Hey everyone, my name is Morten Speller and I'm a researching software engineer at Facebook. This work has been done mainly together with Chupan Wang, who just recently rejoined Facebook. Originally, we were planning to do this presentation together and we'd actually done quite a few practice trials already, but unfortunately, since he just rejoined after graduating from CMU, we couldn't. Apart from Chupan, this has also been done together with Johannes Bader, Andrew Scott, Mateusz Malachitza, Satish Chandra, and Eric Meyer. Now, traditionally, mutation testing is a type of software testing in which we change or mutate certain tokens in the source code and then run the test suite on them to see if the tests catch the changed production code. Then the goal of mutation testing is to ensure that our test suite has a certain quality. What mutation testing gives us is so-called mutation score. However, that single number is hard to cross-compare between different projects, therefore difficult to interpret also for a single project, and it's not really actionable to the individual developer. Moreover, it's computationally expensive because there are many ways of creating mutants at various locations in the source code. Lastly, mutation testing also traditionally uses these very small mutation operators that seem to be like quite artificial faults that don't really resemble real bugs. So what we wanted to do with Mutation Monkey at Facebook was to create realistic mutants at interesting code locations that would drive developers to take action. Now, to make a little joke, we gave Mutation Monkey software engineering level of E-1, which doesn't really exist if you look at levels FYI. And that's because it would submit but never commit these really faulty diffs. Now, at a high level, Mutation Monkey is a machine learning based tool. As such, it has a training and an application step. The goal of the training step is to teach Mutation Monkey a set of templates that it can inject to the source code so that it would produce faults that look like real previously observed faults. To do so, we have to start with preparing a database of such faults. Now, our database consists of basically three principal sources. The first one is defects4j, a general Java database of bugs mined from popular open source projects. We also use a lot of internal code changes at Facebook, including 18,000 bug fixes to production crashes. And then lastly, we get code change pairs from Facebook that led to either a test now being broken or to repairing a test. We then reverse these bug fixes so that they would become error-inducing changes. The next step is to extract commonalities among them by automatically learning and ranking emerging patterns and manually selecting the promising templates from these. The base technology we use to do this is called getAfix, which has also been developed here at Facebook. For Mutation Monkey, we modified it to be getAbug instead. Well, let's talk a little bit about getAfix. So you can find a bit of material on how getAfix works online if you're further interested, but in a nutshell, getAfix addresses the problem of automatically fixing common bugs by learning from past fixes to produce human-like fixes. Instead of an expensive exploration of many candidate fixes, getAfix uses a simple yet effective ranking technique that leverages the context of a code change to select the most appropriate fix for a given bug. In our use case of mutation testing, we use getAfix in the opposite way, to inject human-like faults. Just like Mutation Monkey, getAfix has a data collection, learning, and application phase. Let's start with data collection, which contains versions of source code with a static analysis warning, and a version in which that warning is no longer present through a source code change. getAfix's tree differencer algorithm then finds the precise change on the abstract syntax tree representations of these and feeds it into its hierarchical clustering algorithm. This is able to abstract away differences between otherwise similar fixes to cluster them into patterns. This way, getAfix learns code fix patterns complete with context that can remove static analysis warnings in a human-like way. The nice thing about getAfix is that after the data collection phase, it is agnostic of whether you introduce a bug or simply fix it. So we can just easily turn it into get a bug by simply feeding it our reversed bug fixes. Instead of on a static analysis warning, these were based on crashes, failed tests, etc. In our case study, what we ended up was learning 17 mutation templates from our dataset of reverse bug fixes. Some are as simple as traditional mutation operators, such as changing a literal 1 to -1. Some are more complex, such as removing an entire null check. With these mutation templates, the next step is to apply them to generate mutants. Again, we have to modify getAfix a bit. Now let's look at the application phase. Originally, after applying a fixed pattern, it checks whether the static analysis warning is gone by rerunning the static analysis on it, here seen on the right. In the case of Mutation Monkey, this is our test suite. Moreover, we simply apply a pattern anywhere it fits, so we are not reliant on a pre-existing static analysis warning. What we get from this is not a bug fix, but a realistic mutant. A lot hinges on how well we test our mutants. For this reason, we integrated Mutation Monkey into our internal testing pipeline and treat mutants just like regular divs. Both normal code changes and mutants go through the same rigorous static checks and dynamic testing steps. Of course, we're only interested in surviving mutants in the end. Using this setup, we performed a case study at Facebook for over 3 months, creating 15,000 mutants from 17 mutation templates. Our primary goal was to make mutation testing actionable, so we conducted one of the first qualitative case studies in the field of mutation testing with 26 interviews with Facebook developers. So what does this look like in practice? Here we see one of the code changes that Mutation Monkey submitted and that we would, of course, never really commit. We see a short description of it, and we see the actual mutation that's been made here, modifying the if condition. So in detail, what we got for every single of our 17 mutation testing templates was a kill rate over time, here expressed in %. When we compare them, we see that there's no real large difference between the learned mutation operators. We also see that their kill rate is far lower than typical mutation testing operators, meaning that they perform quite a bit better. We conjecture that observing the code context here was crucial. Now, our developers had an average tenure at Facebook of almost 3 years, but only 1 out of the 26 knew the concept of mutation testing before. So we asked them, does the diff that we just showed you expose a lack of testing? And the overwhelming majority agreed to that. One participant said that he was a bit disappointed that their end-to-end tests didn't catch the mutation. Another one said that Mutation Monkey is a really useful way to prevent those really overlookable bugs that easily get committed. In the next questions, we asked whether such diffs were helpful and whether they were actually going to added tests. And this showed a slightly less positive picture about mutation testing. One engineer pointed out that they indeed plan to write more tests for the part that is mutated, but at this point it would get in their workflow because of all the failing tests. And someone else pointed out that there were already a lot of tests for that, but there were still test gaps and they were aware of that. And they think that that's okay. I want to leave you with this thought, which one of the participants gave us. Said, if this weren't deprecated, I'd create a task to fix it tomorrow, but it's deprecated. So for now, I won't worry about it. How can we as a community create tools that capture this additional knowledge, which is really hard to gather from the code.
Happening. So hello and welcome to the last session. And again, thank you so much for this inspiring video and paper. And we have Moritz with us for this last paper of this session. I'm the session chair, Sigrid Eld, and we already started to fire off questions. What do you mean by an automatic step? And this was answered. Linter static analysis tools that try to remove bugs. Right? So the question was really, is there any data on the mutants that killed in each automatic step?
Yeah, that's a cool question, I think.
Yeah.
So kudos to Rahul. But unfortunately we didn't measure that. And the main reason actually why we went through these pre-steps was to sort of eliminate code that wouldn't look like normal code, and that sort of anecdotally, I would say it's like on the order of sort of 10% of the things that we generated, and it's basically like adding a kind of compile stage before you actually commit the mutants for further testing. So I'd say kind of anecdotally 10%, but we didn't like sort of subdivide it into the various different linters that are being run. That was a bit outside of what was of interest to us.
Okay. So yeah, very cool study. Any other questions from the audience? Did you measure in some way how realistic the mutants are? Michael asked this.
Yeah, so I know that there's sort of recent studies that I think by Michele Tufano that have done try to do that in a way. We sort of Michael, we had this very limited set of mutants that we generated, which is essentially like 16 different mutation operators, and because it's a sort of a semi-automated approach only, so we kind of hand-tuned those further. I would say sort of by construction that they're very realistic.
Yeah, so it's a cool follow-up question, which really links in a little bit what I'm sort of curious about, how you, I mean, you can't really force developers to use this, and I know it's a pretty hard sell sometimes to do this. So with the developers that answered no, will they not add test cases? Do you know why?
Yeah, we do actually. So there's actually a variety of reasons for why not. Some just said, well, our whole argumentation built on the point that the mutants that we would generate had been shown to cause production crashes in the past. And through our study, we learned that argument was not convincing enough, because they said, well, I mean, we've sort of observed almost every imaginable way in which we could crash a system. So just because it happened in production, they were not convinced enough by that argument. And others said, well, I think we've tested that code quite well already, and I don't see a reason for why I would guard against this scenario. And then these are sort of more intrinsic questions, and I would say that there was another category of questions that developers asked us, which is sort of, oh, this code is deprecated soon, and you just can't, I mean, how if there's like no deprecated tag or anything in the code base, how would you know this? And I think actually this is like one of the points to make mutation testing feasible in practice that we need to work on. How do we get these sort of external effects or this external knowledge into there? Because had we known that this would soon be deprecated, we of course wouldn't have included it in the code path that would be sent to mutation testing.
Okay. So is the tool available for others to use?
No, unfortunately not.
No. That's too bad. So how do you expect other researchers, what should they do then to help you?
Yeah, I think actually sort of the general track of what I see people in mutation testing working on is in academia is, I think, really good. People work on reducing computational complexity. I think that's super important. Creating, as Michael said, realistic mutants. We need that. What I think we also need to look into is sort of actionability. I think this was really inspired by sort of the original Google paper on mutation testing. How can we come from this kind of abstract mutation score to something that's concrete for developers? I also maybe see that there haven't been as many qualitative studies. When you, I think now we're at a stage where you can actually, just like we did, apply mutation testing in industry, and then really get some feedback from developers on what they want. So one of the things that we heard from them was actually people saying, "Hey, you just showed me that." Mutation in the program code. Why can't you just automatically create the unit test for that? Why do I have to do that as the developer? And I think such answers can guide us in new and interesting directions. And then I think lastly, what we see in many academic studies is that all that certain mutation of a program is being evaluated on our unit tests. But if you look at an industrial context, that's not at all the case. And once you kind of leave sort of quite well-defined unit testing landscape, it all of a sudden becomes much harder to argue, like which assertion or which test actually even caused this to fail or not to fail. So
yeah, and maybe you can't address something thinking about this near paper that you maybe not can address all important stuff at the unit test level. So that's also food for thought for sure. So
exactly.
There was some other question here about the suggest test cases using EvoSuite like approach. I wonder if something like that would help if you give them baked in test cases. Do you have a reflection on that? You're familiar with EvoSuite?
I mean, yeah, roughly. So I guess the idea is kind of generally with generating tests. So I actually could also suggest test cases using. Yeah, that's true. I mean, there are sort of multiple ways in which you could come up with that. Kind of, I think from an industrial perspective, it's probably not the number of tests that you have that is a problem, in the sense that it's not, the number is not too low. Actually, you probably face the opposite problem. No. You tend to have lots of test cases, and you rather run into the problem of which ones do you actually realistically want to keep, because they need to be maintained and people need to understand what they do, and they shouldn't be causing flaky behavior and so on.
Yeah, I totally agree on that for sure. That was a very good comment. So yeah, I actually been part. So would you recommend others? Do you think the technique and technology and your experience now at Facebook is that you think it's mature enough for most industries to tackle at this point, or?
I think that really, really depends on what the underlying testing culture is. I think mutation testing in a code base that's really mature, that focuses a lot on quality, is useful. If you're somewhere earlier in that stage, it might not be that useful currently. Just because I think the incremental value add of mutation testing in a system that's not already very thoroughly tested is hard to argue for.
Yeah. And of course, they want to know if you cooperated with Google, but you said you were inspired by Google. And I actually have done mutation testing together with Saab. So safety critical system is the really next. Now it's only 10